Good morning. Today I will discuss the questions related to circular motion and gravitational fields, chapter 17 and 18. The first question is to define gravitational field strength. Gravitational field strength is the gravitational force per unit mass. Question B, we want to find the mass of the planet given the diameter of the planet and the gravitational field strength at the surface of the planet. This planet may be assumed to be isolated in space and its mass is concentrated at its center. We are using the equation of gravitational field strength, which is gm over r squared. This small g is the gravitational field strength, which is 8.6. This capital G is given 6.67 times 10 to the minus 11 times the mass divided by r. R is the diameter, should be in meter, divided by 2. So if we convert this into meter, we have 1.2 times 10 to the 7 divided by 2 squared. Then we get mass, which is equal to 4.6 times 10 to the 24 kilograms. The next question is, we have the gravitational potential at a point x above the surface of the planet and the gravitational potential at another point y above the surface of the planet. Now you have to state with a reason whether point x or point y is nearer to the planet. In this case, we can say that this is similar to potential energy or mgh. Here, the planet is the surface. So as the distance or the height from the planet increases, the potential energy increases and vice versa. So I can say that potential decreases as the distance from the planet decreases. And you can also answer potential is 0 at infinity and point x is closer to 0. That's why it is closer to infinity. Or you can also answer potential is proportional to minus 1 over r. The more negative the potential, then the smaller is r. And point y is more negative. So, point y is nearer to the planet. A rock falls radially from rest towards the planet from one point to the other. We want to calculate the final speed of the rock. In this problem, we have to know that the change in potential energy will be the same as the change in kinetic energy. And then the change in potential energy is equal to mass times delta potential. Delta kinetic energy is a half m v squared minus initial v squared, which is 0. So we have here the delta phi, the change in potential, which is 6.8 minus 5.3 times 10 to the 7. It should be equal to a half v squared. So v squared is 5.5 times 10 to the 3 meter per second. Question 2. Explain what is meant by a geostationary orbit. A geostationary orbit is an orbit above the equator, or we call that equatorial orbit. It is in the same direction as the Earth spins, from west to east, and has the same period as the spinning of Earth, which is 24 hours. A satellite of mass small m is in a circular orbit around a planet. The mass of the planet, capital M, may be considered to be concentrated at its center. We want to show that r cubed is equal to gmt squared over 4 pi squared, where t is the period and g is the gravitational constant. And you have to explain your working. Every time you have to explain your working, you can state this: the gravitational force provides the centripetal force. Gravitational force is given by G capital M small m over r squared equals the centripetal force is m omega squared times r. This m is the mass of the satellite because it is orbiting about the planet in circular motion. So this small m, we can cross them out. So here we can substitute omega into 2 pi over period. So gm over r squared equals 2 pi squared is equal to 4 pi squared divided by t squared times r. So we will have r cubed equals gmt squared over 4 pi squared. Yeah, it is used in the next question. We want to use the expression to find the radius of the geostationary orbit about the Earth given the mass of the Earth. So here we can calculate r using that equation. G is 6.67 times 10 to the minus 11. Mass of the Earth is given. The period is 24 hours multiplied by 3,600 to become in SI, in second, divided by 4 pi squared. So the radius of the geostationary orbit about the Earth is 4.2 times 10 to the 7 meters. Number 3, a planet of mass m is in a circular orbit of radius r about the Sun of mass capital M. The small m is the mass of the planet. We have here omega and t, period of revolution. This is the angular velocity. You have to state what is meant by angular velocity. Angular velocity is the rate of change of angular displacement swept out by radius. And the relation between omega, angular velocity, and period is omega equals 2 pi over period. The next question is, we want to show that for a planet in a circular orbit of radius r, the period is given by cr cubed, where c is a constant. Explain your working by writing down the sentence. The gravitational force provides the centripetal force. So you have gm m over r squared equals m omega squared times r. We can cross m out because this is the mass of the planet that is going around the Sun. So we have gm over r squared equals omega is 2 pi over period. 2 pi over period squared multiplied by r. So we have gmt squared equals 2 pi squared is equal to 4 pi squared multiplied by r cubed. And that's where we get t squared equals 4 pi squared divided by gm multiplied by r cubed. And this is a constant. Pi is constant, g is constant, mass is the mass of the Sun, it is constant. So we can prove this expression. And then we have the data for the planets Venus and Neptune given in this figure. And assume that the orbits of both planets are circular. So we want to use the expression that we have derived to calculate the value of period for Neptune. We know that t squared is equal to a constant times r cubed. So I can say that t1 squared over t2 squared is equal to r1 cubed over r2 cubed. So T1 belongs to Venus, and this R1 belongs to Venus also, and T2 belongs to Neptune. This is what we are going to calculate. R2 belongs to Neptune. So we have T2, which is 165 years. And then determine the linear speed of Venus in its orbit. Remember the equation for linear speed, v. V is equal to 2 pi r over period. We know the r for Venus and the period for Venus. So the r is 1.08 times 10 to the power of 8. Oh, sorry, this should be 10 to the power of 11. You should write down in meter. And then the period is in years. You have to convert into SI, which is in second. So 0.615 multiplied by 365 days a year, 24 hours a day, multiplied by 3,600 second in an hour. Then you will get 35 kilometers per second. Now number 4, a binary star consists of two stars A and B that orbit one another, illustrated here. The stars are in circular orbits with the centers of both orbits at point P, a distance d from the center of star A. So the distance from P to star A is d. So the distance from P to star B, to the center of star B, will be 2.8 times 10 to the 8 kilometers minus d. Yeah. Here, explain why the centripetal force acting on both stars have the same magnitude. The gravitational force provides the centripetal force, and then the gravitational force acting on each object is the same, according to Newton's third law of motion. That's why the centripetal force will also be the same, because here the gravitational force will be equal to the centripetal force. The period of the orbit of the stars about point P is 4 years. We want to calculate the angular speed omega of the stars. Use that equation omega equals 2 pi over period. 2 pi divided by 4 years, 365 days a year, 24 hours a day, 3,600 seconds in an hour. Then you'll get 4.98 times 10 to the minus 8 radian per second, or in two significant figures, it will be 5.0 times 10 to the minus 8 radian per second. The separation of the centers of the stars is 2.8 times 10 to the 8 kilometers. You are given the ratio of mass of star A and the mass of star B, and we want to determine the distance d. Here, we realize that the centripetal force experienced by A is equal to the centripetal force experienced by B, because it is stated here. The centripetal force acting on both stars has the same magnitude. So here I have m omega squared times Ra should be equal to mb times omega squared times Rb. Ra is the distance from star A to the center of, from P to the center of star A. Rb is from P to the center of star B. So here we have MA times RA equals MB times RB. RA is equal to D. RB is equal to 2.8 times 10 to the minus 8, 10 to the 8 minus D. MA over MB is given. It is 3. So we can calculate D using this equation, and we get D equals 7 times 10 to the 7 kilometers. Use your answers in AII and BI to determine the mass MB of star B. Explain your working. Again, the gravitational force provides the centripetal force. So we have G MA MB over R squared. R here is the distance between A and B, equals MA times D times omega squared. Here we can cross MA out, then we can get MB, which is 2 times 10 to the 29 kilograms. That's all our discussion about chapter 17 and 18. In the next meeting, we will discuss the next chapter, simple harmonic motion. Thank you. I hope this video is useful.